Morty, we've got to turn the project in early.
Hey, Allie, how are we doing? Oh my gosh, where are we at? We're over here, we're over there, we're everywhere. Early start. Is it early? Is it early? I thought we were late. I don't know. I was getting some more coffee, hanging out with someone really awesome. What up? Good to see you here. What should we do? We could do some chapter 13, review some of the material we just did. Lachey, good to see you here too. Oh no, early start on the project. Oh yeah, so I think we have the project released, right? Because I guess is it... Let's go take a look. I guess Terry has it. Yeah, it says November 30th. So it's already got the instructions on it. Yeah, well, we could take a look. I guess we've kept it. I don't think Terry's making any changes to it then. Okay. Do we look at the project? So let's do it. All right, let's look at some project. I said start the project early. So that's the plan. Stat 201 project. Let's go check it out. Here we go. So here is the project, and you can get points. What is it? +8. This is insane. +8. This is 12% of your grade. +8. Don't have to turn it in late. You don't want to turn in late. +8 is a ton of points. So +8, right? 108. So if you're unhappy with your exam 2 grade, exam 2 is worth 15%. This is worth 12%. Now that's not quite the same, but it's almost like they average out a little bit. Exam 2 is going to have a little bit bigger of a pull, but let's say you made a 50 on exam 2. This brings you up to like a C on the test right here if you make like 108 on it, because you could do this right here. We take 108, times it by 12. We take your 50, if you made a 50, let's say, times that by 15. We add them together, and then we divide by 27. That's a 75 right there. A 75, 76. Does that make sense? So if you get the 108, which means you need to get the bonus, and you need to turn it in early, exam 2 didn't go your way, you can pull your exam score back up to like a 76. That's pretty nice, right? So this is a huge opportunity right here. Start early, ask questions, whatever you made, this is going to help out your grades. 108 is absolutely insane. So with this, what do we have right here? We got some jump data sets. And does Terry have the project instructions? Terry, just delete the project instructions. He hasn't released the project instructions yet. I can tell you about it. I know, right? So that's the issue, is the instructions haven't been released. That's why he should be releasing it here soon. We give more than a week to do it. I can tell you how the project looks and what it's like. So let me show you what it's like. You ready? So we're waiting for the instructions to be released. I'll probably do a big announcement when the instructions are released. But check this out. This is the diabetes data set. So this is the diabetes data set. You ready? So I don't even know what's on the project this semester 100% yet, totally, as Terry's working on it. Thank you. Huge shout out to Terry. Stat 1 coordinator, does a lot of work, gets everything set up. So with this right here, you notice there's some what variables in this data set. What do you immediately notice about patient ID? What do you immediately notice about it? Shout out to Terry right here. Patient ID is what? Patient ID is a what variable? Like, it all comes back to knowing your variable types. It's the identifier. Allie, we got to throw you some points right here. I'm missing the points button. I got to readjust them. I need to make like mid-semester points, end of semester points. That's the identifier. Great job right there. Lachey too. That's the identifier. Then pregnant is, I think, how many times someone's been pregnant, or I forget. It's a bit of an odd variable. This was collected from the Pima tribe. It's a data set that's been out there. And great job, Chase, right there. So we love the points buttons. Woo! Glucose, blood pressure, body fat, insulin, BMI, age are all what variables. These are all what variables right here. Those are all quantitative variables, quantities. So it has to be a quantity of maybe how many times you've been pregnant, or something like that. I forget. Like you look at the data set, it says like it could be how many times someone's been pregnant, but I think the numbers go pretty high. I mean, people can get pregnant 12 times, but that's high-ish. I mean, just what we look at. So descending 17. Yeah, maybe so. It depends. You know, a lot of people ones, zeros, depends. And if we're talking to, just depends, and depends how you ask the question. So some very high numbers right there. At least, I mean, more of like outliers, right? And so with this right here, very right skew distribution on this. Very right skew. There's the extreme right skew. 17, right? So yeah, it's, I mean, to each their own, right? But that's a bit of an outlier, right? It's a very high amount of times. So definitely on the higher end, right? The average right here is 3. The average right here is 3. So the average is 3 and the median is 2, and probably due to the right skew. So you could say, you know, the median, the 50th percentile of pregnancies within this group is 2. So it makes more sense, right? So but there might be outliers. It's, you know, it all depends. Think especially like my mom came from a family of 5, and that's kind of large-ish. But I've known some people who've come from families of double digits. So you know, each your own. That's what I say. So those are all quantitative variables right here, and then we have categorical variables. So with these categorical variables, they require different analysis. We'd be looking at proportions, like what percent of people are considered older. Oops, we don't want to do fit y by yet. Fit y by x yet. So we go to analyze distribution, and we go to age group, and we can see the proportion of people who are older and younger. And we're actually getting from this family of 9. Wow, yeah, that's a lot right there. It's, I mean, at least to us, at least I consider it a lot, but people back then might be like, 9? Your family's a little tiny family. So this is the proportion right here. This right here could be known as what value. That prob right there could be what value. Because if young 316 is x and this is n, that value mathematically is what in notation. This is good notation practice to know that this is what. That's p hat. That's the sample proportion, right? So that is the sample proportion, and that could be called q hat. And you know what we can do really quickly inside of JUMP? Really easily and quickly, we can go here to the red arrow and go to confidence intervals and select the level of confidence. So we can go to a 90, 95, 99, other, maybe we want to enter in like a 92% confidence. And there you go. I am 92% confident. The true proportion of people in this group that are called younger or describe themselves as younger is contained in the interval 76.8% to 83.8%. I am blank percent confident that the true blank is contained in the interval blank to blank. Nice and easy, right? So what if we wanted to estimate the true body fat of this group? What if we want to estimate the true body fat of this group? To estimate the true body fat, we'd go to analyze distribution. Now, distribution is used when you're analyzing how many variables. This is a good review right here. Great job, Ali, right there. Yep. So analyze distribution is used when you're analyzing how many variables. The numbers, yeah. And this is analyze distribution also. And there's the numbers, 76.8% to 83.8%. Portion of younger people. Yep. So analyze distribution is used to analyze how many variables at a time. It's not fit y by x. Analyze distribution analyzes how many variables at a time. So it's not fit y by x. Analyze distribution just does one. So it's your univariate analysis. Does that make sense? So fit y by x is a bivariate analysis, which is right here. And this is univariate. So that's univariate. And then this is bivariate y by x. Yep. So it kind of helps when you're like, JUMP makes life easier. It's point click, and it does things like, oh, we want to look over here at the body fat of these individuals, and here it is. Body fat's kind of normally distributed, right? Some outliers. Let's go ahead and stack this with the red arrow where our options are at. Thank you so much. Yeah, JUMP's pretty good. That's why we use JUMP for our class, that way you don't have to code. It makes life easier. All this can be done inside of R, but JUMP's going to give you all your summary statistics and everything pretty quickly. And look at what we instantaneously have. And Ali, if you really know what we've been learning, you can calculate the margin of error for this interval like this. And I just want you to estimate it. So take a moment. If you're really knowing these chapters well, don't worry about being exact, but what the margin of error for this interval is basically what? So for this right here, can you quickly calculate the margin of error for this 95% confidence interval. And so look at the interval. The interval is 28.1. You'll be interpreting just like this. So I'm kind of doing the project right now. I might be doing, because I don't know exactly what's on it, but I'm kind of doing it a little bit here by looking at this and interpreting it. So what would the margin of error of this interval be? You don't have to be exact. I just want you to kind of round it. You're like, oh yeah, it's kind of that. Oh, close, Ali. So it's not 2. And I'll show you here. Great answers, Ali. Got to throw you some points. You'll see why it's not 2 in a second. And I'll show you how to find the margin of error. So the margin of error, and we'll go for 2,000 points for those good guesses right there. The margin of error is not the length of the interval. The margin of error, I think I drew it out earlier, is always what the length of the interval. So the margin of error won't be the length of the interval. Like if I told you, if I buy a steak dinner, it costs between $40 to $60. Ali's seeing it. What would the margin of error of this interval be? So this steak dinner has a lower estimate of $40 and a high estimate of $60. The margin of error would be what? What would the margin of error be? It'd be 10. And then how would you describe this? If you'd say, yeah, it's about this plus or minus this. So you'd say, I estimate it to be about this. Like I estimate the price of that steak to be this. Like you're saying probably close to about this for the steak, right? Plus or minus 10, yep. And then what would be the center of the interval, which is the estimate? The estimate of the interval, what is the estimate or the center of the interval? The estimate is 50, yep. There you go. And that's actually, if you divide the numbers, you can get the estimate. So the formulas are upper minus lower divided by 2, which is half the length of the interval, is equal to margin of error. And it's really good to kind of like see how these are done, just so you understand. And then upper plus lower divided by 2 is equal to the center of the interval. And does that make sense why it'd be the center? Because like 40 plus 60 is 100. Divide that by 2, you get the center. So you're just averaging the interval together. And then half the length of the interval is going to be the margin of error, to be like, well, let's look at the full length of it. So understanding it mechanically like this is really good. And so think about this. When you look at this interval on the screen, the margin of error, well, the interval goes from 28.1 to 30.1, basically. So the margin of error is 29 plus or minus what? Like, just call this 29, call that 28, call that 30. The margin of error is basically what right here? So it's basically 1, right? Because you could say, the body fat of these individuals is close to 29 plus or minus about 1%. I mean, you could throw the 29.1 to 30.1 to 28.1. If you want to do it exactly, it's 1.04 or so. But does that make sense if you just think about it and you look at it and you say, well, it's about 29 plus or minus 1. Like just understanding it conceptually is a huge part of it, to see it and to understand it. And then how would you interpret this interval? Nice job, Ali, right here. How would you interpret this? This is really great practice. So try to do your I am blank % confident that the true blank is contained in the interval blank to blank, and think what you're trying to estimate. They give you hints right here of the context. So try to interpret this and you'll really get down. Then we'll do a third one right here and you will have all the confidence rolls for the test you'll have seen. So how would you interpret this right here? You'll have seen all the confidence rolls for the test once I do the third one. And don't worry about getting it wrong. Just take a shot at it. And this is I am. Oh, be careful. So this one is not proportion, though, because we asked them how much body fat do you have on you. So this one right here is not proportion. We're going to throw you some points for that. This one here is not proportion because we asked them how much body fat. And I said, oh, my amount of body fat is this. Like, so we're trying to do amount of body fat. So this was a quantitative question, like how much body fat do you have on you? And the answer is a lot. The true mean, exactly. So give it a quick revision, do a copy paste quick revision, and then you'll see. So you basically have it. And so this would be what? You basically have it right there, Ali. Great work. Good practice for the final. Because that's one of the biggest errors that happens on these is people put proportion instead. I mean, I am 95% confident that the true, and then one word, Chase, this is so close. And Ali has it right there. I am 95% confident that the true mean of body fat is contained in the interval blank to blank. Exactly. And great job, Chase and Ali. More points in the chat. That's exactly what you want to put. Chase and Ali, your answers, great job right there. And this is an interval to estimate the true mean. Now there's a third interval. The third interval, let's look at what it does. There we go. And great job, Lachey, right there. Good practice for the final on interpreting, which we are going to have to write out. The third one is going to analyze two variables. This is the chapter 17. So this is chapter 17, a little bit further down the road, probably the last second to last, or the penultimate week of class, meaning second to last. Let's go right here and do the following. I don't know how much I'm doing things on the project, but let's look at this right here, and let's do the following right here. Okay. So this interval, what is this interval looking at? I want you to just take a moment and say we're analyzing this and this. We're trying to understand this with this explaining it. I know it's end of class review. So we're trying to understand this with this explaining it. Talk to me a little bit about this analysis. Just look at it visually. Talk to me about this analysis you see on the screen. This was the fit Y by X with age group in the X and body fat in the Y. So what do you see here? And then what does it look like for the older people? Just whatever that's trying to tell you, maybe. What do you think it's trying to tell you about older people? That's Allie, good. And that's the R squared, right? Maybe I was going towards some R squared, which we don't interpret for this, but you do get an R squared. Good points right there, Allie. It only explains about 1.2% of the variation, like someone's age group, which is the X, only explains about 1.2% of the variation in their body fat. So there's a lot of variation in body fat that's not accounted for by these variables. So you can literally use the R squared and interpret it, which isn't on the final, but hey, it's good knowledge. It's R squared. R squared adjusted for how many variables in the model. We don't do that in 201, but we do it in 320. A lot of 201 knowledge carries over. The body fat is higher with the older age group. You are correct. If you take a look at the analysis right here, you see how it says younger minus older. Do you see how it says younger minus older? So if older is higher, then this difference will be what? Younger minus older. Oh, we did a pooled. 2 seconds. We're not supposed to do the pooled. T-test. There we go. So it's negative. Does that make sense? So since we're doing younger minus older, because it's negative, older was higher. If it's negative, the second one is higher. So what is your best guess for how much more body fat percentage-wise older people have? What is your best guess? Just take a guess and say, older people probably have about this much more body fat than younger people, like percentage-wise. You could round it. Give me your best guess of the difference. Probably about 3%. You see how that says difference? It's your best guess. Now, do you think they have exactly 3%, or maybe, I don't know, the true difference might be somewhere plus or minus this? Our best guess would be they probably have about 3% more body fat, right? But if you had to give some plus or minus on this, how would you interpret the interval? We got to give a margin of error, right? So now we say, I am 95% confident that the true difference in mean body fat of older and younger people is contained in the interval negative 0.5 to negative 5.4, with younger people probably having less body fat. Does that make sense? So, or we could say with older people having more body fat. I am 95% confident that the true difference in body fat between younger people and older people, you could say younger minus older people. Sometimes that makes more sense to do it that way, to like write a little bit mathematically. The true difference of younger people's body fat minus older people's body fat is contained in the interval negative 0.55 to negative 0.4542, where older people probably have more body fat than younger people, because 0 is not contained in the interval. So there seems to be a statistically significant difference. P-values for chapter 17 also. So with this, can you calculate pretty quickly the margin of error of this interval? I've got an estimate in my head. See if you can calculate the margin of error. There's quite a few ways to do it. Who here can tell me the margin of error of this interval? There are questions just like this on the test that show you output like this. We are 95% confident that the true difference of younger people's body fat minus older people's body fat can be found in the interval. You might say true mean difference. Yes, true difference in means might be. True difference in means. Allie, we're going 3 big points for that. I'm just going to add one thing here, that the true difference in means, because we're looking in means. There we go, in means. Great job, Allie. You did it. That looks to be accurate. And great job, got 3 more points. The margin of error can be found half the length of the interval. You can also, for the margin of error, another way to calculate it is to take right here the center of the interval of 2.9862 and subtract out the lower. And that'll give it to you right there. So it's 2.45 about. Or you could take half the length of the interval. So 5.42. It doesn't matter if we do the negative or positive. We just need their distance. And there it is right there. Yeah. How are people doing this? We just did 3 chapters. Like we just went boom, boom, boom. I am blank % confident that the true blank is contained in the interval blank to blank. And the only 3 things we put there are true mean, give context, true proportion like we did today, give context, and true difference between the means. Boom, boom, boom. And so that's a lot of it. And then we've got the test right here, which confirms that there is evidence of a difference. This one checks to see if there is a difference. This would see if younger people are less than older people, and there is statistically significant. Margin of error is upper minus lower divided by 2. Exactly. Great job, Allie, and good practice. So don't fear the project so much. We kind of did maybe half-ish of it. Probably a lot of the material on it was covered here. But the project's going to use one of these data sets. You'll pick which data set, you'll write the report, you'll answer the questions, and you'll need to put an executive summary and a future research. You can always send those to me to have me look them over. What other questions do people have? Let me know your question. Lots of review. Good stuff. Good stuff. If you're following along with that, you understand the material well. That was a review of chapters we haven't even done yet. But it's all built off of the ideas of like what are confidence intervals, what are margins of error. So if you know how to find the margin of error, it's half the length of the interval. If you know how to find the center, it's the 2 values averaged together. Can I start your project? Of course, yeah. So send it to me early, and then I give it a quick scan. I won't read everything, but I'll give it a quick scan. And if it's close enough, sometimes I even grade it and give you the 100 anyways, or the 108 with the bonus. But do it early. Do it early. It should be coming out here within a week or so. Within the week, I hope. Let me see if we've got the decision on extra credit yet. Nothing on extra credit yet. No decisions on extra credit yet. No decision on the extra credit yet. When will the extra credit come out for the bonus? Need more practice? Practice on what? Whatever you want to practice, we can do it. Name it. We can cover it. Slept like 9 hours last night. Still tired. What's the project? Let me know what you're working on. We can start covering it. Good. What chapter shall we cover? We could do chapter 13 homework. I do the whole thing. We got that going. Yeah, let's do some homework, Lachey. That's a good idea right there. I was thinking the same thing. Great minds. Alike. You got to log into my Pearson. Let's do some chapter 13 homework. Chapter 13 Simon Mitchell. Mewbot talking away in the chat. Mewbot. Bed Bath & Beyond. What? New coupon. 20% off a single item. Gosh, I'm gonna get some cucumber melon. Some, was it plumeria? Some juniper breeze. Some good stuff right there. Here we go. Let's start out the homework. 2653. Stat 201. Chapter 13 homework. Question 1. Let's go check it out. Here we are with some Pew Research. In 2018, they pulled a random sample of 1,058 U.S. teens aged 13 to 17 about internet use. 45% reported that they went on the internet several times daily. Really? I'm sure it's much higher than that now. A fact of great interest to advertisers. The 95% confidence roll for this number is 42 to 48. So how do we interpret this? Know how to write this out on the test. I am blank percent confident that the true blank is contained in the interval blank to blank. You want to be able to write it down. So don't even look at their answers yet. It was 42 to 48. We're trying to estimate the true proportion of teenagers who go online. So I am 95% confident that the true proportion of teenagers that go online is contained in the interval 42 to 48% that's 45 plus or minus 3%. They might be getting to that right here. So let's see. One is 95% confident, not of the polled individuals. That's wrong. One is 95% confident. If one were to ask all teens, that's the truth. Okay, that seems right. There's a chance no. So they're getting at the point that the interval is trying to estimate the truth for all individuals. It's not for the sample. We know the answer for the sample is 45%. So it's not about the sample. When we talk about 95% confident, we're trying to estimate the truth for all individuals. That's why, and I don't love their interpretation right here, I'm 95% confident that the truth for all individuals is contained in the interval blank to blank. Explain what the meaning of 95% confidence means. We went over this a little bit in class today, where 95% confidence means in the long run. So it's not about one interval containing the truth. 95% confidence means if you were to make 95% confidence rolls, 95% of 95% confidence rolls are expected to contain the truth. So let's see right here. If one collected many random samples of teens, about 95% of the confidence rolls one construct would contain the true, it says true sample proportion. That better not be the right answer. If one collected many random samples of this size, about 95% of the confidence rolls one constructs would contain the true proportion. Yeah. The true sample proportion is not a thing. The sample is what we observe, and we're trying to see if the true proportion is in there. So true sample proportion should never be said. I was like, there's no way that's right. You would never say true sample proportion. I mean, it is true. It is your sample. But when we talk about true proportion, we're talking about the actual reality for all teens. And if we were to repeat this process many times, collecting 95% confidence rolls, 95% of 95% confidence rolls would be expected to contain the truth. So it's not about one interval containing the truth. See, they're saying like here, there's a chance that it contains the truth. No. It's about the repeated process of creating 95% confidence rolls that we would expect 95% of 95% confidence rolls to contain the truth. And we've kind of written test questions like that. So a little teaching the test moment. Next question right here on the homework. Chapter 13, homework, question 2. Reaching out 2 standard deviations on either side of the sample proportion makes us blank percent confident. Now, 2 is about the answer. I know where they're going with this. So what is the actual z-score for this? 5,000 points if anyone listening knows the actual z-score for this confidence roll they're talking about when we reach out about 2 standard deviations. It should be reaching out about 2 standard deviations. It's talking about making a what percent confidence interval. So remember, try to know these answers before clicking on them. So think of your 68, 95. That's what it's speaking about, the empirical rule. And this is the z-score used to make 95% confidence roll. So it is 95, correct. And then the actual answer, got 30 points there, Lachey. Great job. So this makes about a 95% confidence roll, and the exact answer is 1.96. So the exact answer for this, we need to go to the David M. Lane applet. Let's go check out the David M. Lane applet. So if you wanted to know the exact answer, you need to go to these applets and use them. So there's just the questions. And then you click the second button right here. Then you put in the third button right here, and you do the confidence roll for 1.96. It's 1.9445, or 45 is basically 2. So that is the actual number for 2. But if you want, you should be using 1.96 to be exact. But this is where we get the 68 is basically 1. 95 is basically 2. 99.7 is basically 3. 99.7. 68, 95, 99.7, 3. So with this right here, 95% confidence rolls are basically 2 standard deviations. When I do them in my head, I use 2. So it's very close to 2. But when I do it on the calculators, it's going to use 1.96 for the z-score. So very good question right here on using the empirical rule as it says right there with the problem. This one wants the margin of error. You don't need to memorize them. We will give them to you on the test. So we would give you values on the test. So you can see right here, I wrote some of them down today during lecture. I wrote them on the side of one of the slides, I thought. We talked about it right there. And here's the values right here. These are some of the values: 1.282, 1.645, 1.96, 2.3263, 2.5758 are the values respectively going up right here. And as we get more confident, the z-score increases, which makes a larger margin of error. We will give them to you on the test, and we don't use z-tables on a test. Good job. Yep. And then also remember, you can look up any of them by going over here to the David M. Lane applet and typing in something like 99 and getting the z-score right here for your confidence interval. And look, we need one of them right here. And this problem right here, let me take a note on it, is really going to boil down to knowing your what. What is going to be the key in doing this problem right here? How are we going to get this problem right? How in the world are we going to solve this question? It all boils down to knowing your what here. This question really boils down to knowing your what. Knowing your what. The notation, let's say you got it right there.
Notation, brother.
Notation, brother. It's all about notation for many of these problems and conditions, all that good stuff right here. So here we are. We need to find the margin of error. The margin of error from the formula sheet is everything after the plus or minus. So since we're doing proportions, it's p hat plus or minus z star p hat q hat over n square root. So let's start with the easiest one. What is n? You can tell me what it is or the numeric value, but what is n right here? You can tell me what it is or its numeric value, but what is n? And we only need the margin of error. So I'm going to go ahead and delete this off because the margin of error is what we're calculating. It's everything after the plus or minus, because like plus or minus a certain amount is a margin of error. So what is the value of n right here? Use the problem above to find what n is, and then you can tell me kind of conceptually what n is, or the numeric value in the problem above, but it comes down to knowing the notation and plugging it in. So what is the value of n? And do this, if you don't have it right now, write down n on a flashcard and then put it on the other side what it is. So what is n? N is going to be what? So n is sample size. So what is our sample size right here? What is the size of our sample? Give me a second or two more. N is sample size. So what is the size of our sample? What is the size of our sample? There we go. Now we need to find p hat. What is p hat? P hat is sample proportion. So sample proportion is the proportion in our sample that conform to the question or answered in the affirmative. So the sample size, they polled 1,997 registered voters. So that's the size of the sample right there. It looks like a year, but first time I read it, I thought it was talking about 1997. That's how many individuals they spoke to. They spoke to 1,997 people. And then the p hat is the sample proportion. So we're trying to figure out what percent of people think the country's going in the wrong direction for the whole population. So what is p hat right here? P hat is the proportion in our sample. I know, right? A little tricky. The p hat is the proportion in our sample who think the country's going in the wrong direction. P hat stands for sample proportion. So what is p hat? P hat stands for sample proportion. What is p hat? What is p hat? What is p hat? It could technically be one or the other, but preferably, since we're trying to figure out what percent of America, and since we're interested in what percent think we're going in the wrong direction, that's kind of the one we're interested in. P hat's the successes, so successes thinking we're going the wrong direction, and then the complement of that is kind of not the wrong direction, not right direction. So that's the complement right there. We're going to use them as percentages too. So the last thing we get to here is what is the Z star? the star on the Z means you need to make it relative to, got the hiccups. The star on the Z means you need to make it relative to your confidence level. So, Lachey, do you remember the Z star that we need? What Z star do we need for a 95% confidence interval? So if you have from the notes, or if you go to the David M. Lane, lots of ways to get it right there. The exact Z star we need is what? And you can use the David M. Lane. I'm showing lots of ways to solve it right here, but you want to either go to the David M. Lane, have it written down. We will give it for you on the test, and it's 1.96 right there. Check out the David M. Lane on how to get these. Have them written down. We will give them to you on the test, but you can get them right here with my Pearson and all this to solve them. So now we put in the values of 1.96. That was found via David M. Lane or the applets, or the writing it down, 7.48. Do these as decimals. You want these to be decimals. Complement of p hat over square root, or over sample size square root. So let's go ahead and take this right here. And 0.748 times 0.252 divided by 197 and square root. That is now the standard error. This quantity right here is known as standard error. Multiplying it by the Z star turns it into the margin of error. And so bring it over here, drop it into 3 decimals. And there we go. Check answer. Good to go. Explain what this means. So one is 95% confident that the observed population proportion, the proportion of adults that responded were in the wrong direction is within blank percent of this one right here. So we're trying to, that the observed proportion of adults that responded, no. Okay, let me see. Within blank percent of the sample portion. Shouldn't say observed, should say true. Probably that any given adult. No, that'd be so it should be this one. Yeah, because from the sample proportion. And I'll show you why. Oh my gosh, wait, what? Oh. Yeah, I just did this one earlier today. Need more coffee. Don't you tell me I'm wrong. Let me read it again really quick. Let me go back. Brian makes an error. No. One is 95% confident that the observed proportion of adults that were wrong track is within 0.0 of the population proportion. Just don't even like the way that's interpreted. Because the population proportion is the truth, and what we observe is from the sample. So I would never interpret it that way. Yeah, I really don't like the way they interpret that. That would not be a good interpretation. When they say observed, because that's what got me tripped up, but the sample proportion is the estimate. So it should have said one is blank percent confident that the true proportion, sort of throwing curveballs at you. Yeah. Because the estimate is from the sample. Ma Pearson, darn you, I just did that one earlier today. Check out earlier today where I didn't make the error. So earlier today, we did it over here. One of these, I think it was this first one right here. Or one of those, we did it, and we didn't make the error. Every once in a while, we make an error. So that's why we practice, and you can redo the homework questions multiple times. So here we are with a 90% confidence roll. What do you think this question is going to boil down to when we make 90% confidence rolls? This whole question is going to boil down to knowing your what. This whole question right here is going to boil down to knowing your what. All these questions right here, especially when it comes to the test, is really going to boil down to knowing your what. So you got to be able to mark it all when you get to the test. You have to know it. Got to know
Notation,
that.
brother.
Notation, brother. Let's go check it out over here. And let's see. So this one wants us to make the 90% confidence roll. And so with this, we need to do p hat, which is the sample proportion, plus or minus z star, which is based on level of confidence, the z score, p hat, which is the sample proportion, times q hat, the complement of the sample proportion, over n. Complement is found by 1 minus p hat. So the sample size, easiest thing to find, is going to be the amount of people they spoke to. Then we have the proportion in the sample that corresponded to what they're interested in. Then we take the complement of this and do 1 minus 0.517 is equal to 0.483. That is Q hat. 1 minus P hat is Q hat. So now that we have Q hat, that'll be plugged in. Make sure to do these as decimals. And then the last thing to find right here, Lachey, do you know the z-score? The z-score is relative to 90% confidence. So you need to make sure if your question says 95, use the 95% z-score. But this is going to be smaller than the 95% z-score. This z-score is what? You want to go to the David M. Lane applet if you don't know it. So the David M. Lane applet is one of the great ways to look up z-scores. And so you want to go over here and punch in 90%. Make sure it's set up the same way as mine, where you're on the second button here and the third button here. And with everything clicked in, the z-score is 1.645, and it doesn't change for z-scores. Great job, Lachey. Good practice. The z-score is 1.645, and really this problem becomes just plugging in the numbers now. 1.645. The p hat is going to be 0.517 plus or minus. Remember, everything over here is the margin of error as you calculate it. The p hat is the estimate. Just good notes to have. How are you feeling, Lachey? Is this chapter seeming a little bit easier? It's very repetitive. So just the practice is what helps. And then knowing how to find your values, knowing what it means when you make the interval, and then just solving it out. So there's the values. And whoops, Photoshop. Every day I click Photoshop. Every single day. Close down Photoshop again. Closing Photoshop. Close Photoshop. There we go. Good job, Lachey. Yeah, it's just practice. Like, person said, practicing the homework for the test was a big help for them too. And that's the standard error times 1.645 is the margin of error. So 0. And then plus or minus. There we go. And so let's take these values, times them by 100. 51.7, because I think we have to. And then 1.22. There we go. Those are in percentages now. Those are the margin of error. So 51.7 plus or minus 1.2. So 1.2 is not going to change it enough, right? Should be able to go 57 plus or minus 1.2. Wait, it's not 57. How did I get 57? It's 51.7. There we go. 51.7, it wants to 2 decimals. So 51.7, 52.9, and 50.5, because I think all are rounding. Woo! So once again, all I did right there was do the plus or minus. I was doing it in my head. So I went 51.7 plus 1.2, because it's only to 2 decimals. Be careful that it doesn't round on you. 51.7 minus 1.22, and that rounds to 50.5. Double, carry your decimals to the end. Be very careful. Easy errors to make. So here we are with our interpretations. I am blank % confident that the true blank is contained in the interval blank to blank. One is 90% confident that the probability of not a randomly selected Californian. One is 90% confident that the true proportion of Californians who consider moving out of state is between the interval blank to blank. Okay. There we go. We're trying to estimate the true proportion of people who consider moving out of state. So I am 90% confident the true proportion. If there is more than 50%, they're going to try to do something. So do you think the truth is more than 50%? Because we think it's somewhere between 50.5 to 52.9. So I would say, since the confidence interval is greater than 50%, the state should consider this thing that they're going to do. And that is because they're going to do it if it's more than 50%. So if it's reasonable to say that more than 50% of Californians meet this criteria, then we should consider this. So since the interval is greater than 50%, we have evidence that we should do this because they're looking to see if it's greater than 50%. So good stuff right there. Question 5 looks to be a short one, just a conceptual idea. Fall to 6, 23, Stat 201, Chapter 13, Homework. Question 5. Which of these statements interprets the 95% confidence properly? Let's go look at our notes again. 95% of 95% confidence intervals are expected to contain the truth. So that's what we're looking for basically, is that it's about the long run process of making multiple intervals. It's not that one interval has the probability of 95% of containing the truth. It's that if you were to do repeated trials of making intervals, In the long run, you would see 95% of 95% confidence intervals contain the truth. So it would be in the long run. 95% of the time, the sample proportion will be in the interval. 95%. Great job, Lachey. Following along, got 3 more points for that. That is the answer. 95% of samples will produce a confidence interval that contains the true proportion. So that's exactly what you see right here. These are different samples. So 20 random samples. So in the long run, repeatedly doing the process. It's not about the sample proportion being the interval 95% of the time. 95% of samples will produce intervals that contain the truth. So 95% of 95% confidence intervals, about 95% of confidence intervals that are 95% will contain the truth. So that's the thing right there. 95% of 95% confidence intervals are expecting the truth. So if you do the process repeatedly, then in the long run, you'll see it. So that's really good right there. That's just the thing. It's odd to say 95% of 95% confidence intervals are expected to contain the truth. It's not about one interval having a 95% chance. It's about in the long run, the intervals will contain the truth, like repeatedly over the long period. This one's pretty quick and easy again, too. As the confidence increases, or as the level of confidence increases, the confidence interval will do what? So don't click the button, though, but just tell me conceptually, as the confidence level increases, the confidence interval will get water. So as your confidence interval increases, your confidence interval will get water. So the confidence interval will get bigger, get wider, it will contain more values. Think you're more confident, and this is the value of Z that you're working with right here. The value of Z controls your level of confidence, so we put the star on it. So when you go to a higher confidence level, Z gets larger. At larger values of Z, you're more confident, and you cover more of the interval. So just looking at it visually, you can see what happens if you increase Z. So watch right here as we go to 95%. 95% is going to make the interval wider, and Z gets bigger. 99% makes the interval wider, and it gets bigger. 60 or 70% makes the interval smaller, and Z got smaller. So it's very close to 1 because they're related to Z scores. 68, 95, 99.7, and we're using the David M. Lane applet. So as we get more confident, the interval gets wider. So we should have that one right there. Good conceptual stuff. If the level of confidence increases, the interval gets wider. So good stuff. To have a higher confidence, there must be a wider trap. Sure, cool note. Oh my gosh. Whoa, look at these assumptions. Okay. So what are our conditions right here? Let me take a quick note on this while we think about the conditions. The conditions are random, and sometimes they break it apart into independence, which is basically random. Also, random, 10%, at least 10 successes, at least 10 failures. Be careful when doing the conditions because the third condition will depend on the type of variable you're working with. So when you're doing quantitative data, it'll be nearly normal, large enough n. When you're doing categorical data, it'll be success failure. So here we go. A poll conducted by the UC Berkeley Institute of Governmental Studies in 2019 found that 52% p-hat, 52.3% of respondents from the 4,527 respondents sample size said they considered moving out of state. So first question, did they take a random sample? Well, that would be a reasonable assumption. I would say, I don't think this is not a simple random sample. Oh, they're saying no because this is not. Select multiple. Oh my gosh. A poll conducted by UC Berkeley. I would assume they took a random sample. Next, we have to know that this is less than 10% of the population. So we have to ask, how many people live in California? Because we're trying to look at UC Berkeley, which is California. Is 4,527 people less than? What is the population of California?
In 2020, the population of California was 39,538,223.
39 million. Is 4,000 less than 10%? Yes. And we'll do it as a percentage. It's about 0.01%. Exactly. So we've sampled way less than 10%. And then the last condition is, do we have at least 10 successes, at least 10 failures? This condition is checked by doing n times p hat. We'll show that here in the notes. So you need to find n and you need to find p hat. So the last condition is the np hat, nq hat. at least 10 successes, at least 10 failures in the sample. So n is 4,527 times 0.523. We have that many successes, and our failures right here are going to be more than enough. This is the percent of failures, I believe, and then we times it by the sample size, and there we go. So I would say yes, all the conditions are met with reasonable assumptions. I really wish it said random, but I guess they're thinking it's a poll, so probably random. If for some reason you selected no, it's not a random sample, let me know. I'd give you your points back. Everything else is obviously met, but all conditions assumptions are met, so I'd say good right there. The margin of error for this proportion of Californians would be considered moving out of states for 90% confidence interval is 0.012. Would the margin of error be larger or smaller for an 85% confidence? So when you hear 90 to 85, are you getting more or less confident? When you hear 90 to 85, are you getting more or less confident? So this relates to the z-score used to calculate it. That would be the only change to the formula, which it's not asking us to do it. It's only talking conceptual. When you hear 90 to 85, are you getting more or less confident? You're getting less. So the z-score would now be water. So when we go 90 to 85, the z-score is getting water. And think this is part of the margin of error in the formula. So the z-score is going to be water. You're less confident, so the z-score is going to be water. We can see it here with the David M. Lane. Since you're less confident, you go from 90 to 85, the z-score is going to be smaller. And so since the z-score is smaller, and it's part of the thing you multiply to make the interval, your interval is going to be water. So here's 90. There's 85, and you can see it right there. So since you're going from 90 to 85, your z-score is smaller, your interval is going to be water. And that's the concept they're trying to get across right here. So there we go. Let's see. It's going to be smaller interval. So the margin of error produced, but would this margin of error be larger or smaller for 85? Okay, for 85. Okay, just got to make sure they're talking about the 85. To be less confident, the interval needs to contain the true proportion less often. So we're down to these two answers right here. So the margin of error would be smaller. Good stuff. That's it. That was easy. So yeah, to be less confident, the interval needs to contain the truth less often, so the interval would be smaller. That's the way it goes. Good question. Good review of how to do it. Okay, so let's see right here. It looks like another conceptual one. 54, 43. Okay. Several factors are involved in the creation of a confidence interval. Among them are the sample size, the level of confidence, and the margin of error. Which statements are true? Ooh, these are good ones. Okay. For a given sample size, higher confidence means smaller margin of error. For a given sample size, higher confidence means smaller margin of error. Confidence is controlled by the what? Right now, confidence is controlled by the what? What is the confidence controlled by? Confidence level is close. Good guess. Not by the p-hat. P-hat doesn't control confidence level. What controls confidence level? Confidence level is controlled by the what? You get to pick your confidence level. So which of those do we get to pick? Well, margin of error has a component of the confidence level. So the margin of error has a component of the confidence level, but the confidence level is specifically controlled by the what? We get to pick it based on how confident. I mean, like when we say I'm this % confident, we then use the thing relative to that. So the thing that really controls the confidence, which is part of the margin of error, is the what? In this formula right here is the what? It's not p-hat, it's not q-hat. What controls how, like, I am this % confident, and then we take that value based on it? Like, I'm 95% confident, we then find the what related to that. Like, we'd say 95% confident, we need to go find this thing related to that. And that controls the confidence, basically. The z-score, yep, great job, Lachey. Excellent work. And the star means you get to pick it based on confidence. So for a given sample, which just means like same sample, higher confidence means, so if z-score were to go up, what would margin of error do? If the z-score got bigger, went from like 1 to 2 to 3, what would the margin of error do? So it's saying higher confidence, which means bigger z-score, like 68, 1, 95, 2. So as you get more confident, what would happen to your margin of error? So if you plug bigger values in for z, which mean more confident, what would happen to the margin of error? I've seen things like this on the test. It'd get wider, which means margin of error is bigger. So this is false because it's saying it'll get smaller. That is a false statement because as we get more confident, the interval gets bigger. Be very careful. They do flip where the trues and falses are at sometimes. Maybe they fix that this semester, but sometimes false is on top. For a specified confidence level, larger samples provide smaller margins of error. So it's basically saying everything else the same. So larger samples. So let's look at this. You ready? P hat plus or minus Z star So what happens to the margin of error? What happens to the margin of error as n gets bigger? What's going to happen to the margin of error as n gets bigger? Because you're dividing by n. So larger samples provide smaller margin of errors. What's going to happen to the margin of error as n gets larger? So you're dividing by n, right? So if n goes from like 1 to 2 to 10 to 50 to 100, then it'll make that value wider because you're dividing by it. That's the key right there. You're dividing by sample size. So what is going to happen here? Try writing down the formulas. Make sure you know the notation because you have to know where the margin of error is in this formula. So you have to be like, okay, mathematically speaking, plugging in, it's going to make it smaller, right? Because you're just dividing by bigger numbers. So larger samples provide smaller margin of errors. That is true. So it is a fact that if n increases, margin of error decreases. And so this is a true statement. For a fixed margin of error, larger samples provide greater confidence. Now, this one is one of the toughest ones because it's saying for a fixed margin of error. This one, first semester I ever did it, threw me for a loop. So we have to think about the following. For a fixed margin of error, it's saying margin of error equals something like this. And margin of error is Z star P hat Q hat over N. So fixed means it has to, the margin of error has to stay the same. Very tricky question. So larger samples. So let's say everything works out here with n equals to 10. Like this math works out right now. Whatever we solve out at the top, it solves to 0.04. So down here in this equation, n should be what theoretically? So n should be what theoretically? Like if everything's working out, just theoretically, if everything's working out, n should technically be the what? So theoretically speaking, if everything works out here mathematically with n of 10, then n should be what? Theoretically. Like if we just have the same thing. Hint, that's a hint right there. So if everything works out up here mathematically, then if everything down here works out mathematically, n should be what? Because like maybe it still works out, right? So n should be the same, right? But what if hypothetically it says larger sample? So n is still sample size, right? If every other value here is the same, down low, if all these values down here are the same, would this equation work out? If every value is the same as the top ones, will these equations still work out to margin of error of 0.04? Will it still work out, yes or no? If like the top one mathematically solves to 0.04, if you plug in the rest of the numbers, it solves to 0.04, then with the bottom one here with a larger n, will it still work out to be 0.04? mathematically? Will it still work out? Because everything else we're saying, if everything else is the same, like if these values and these values stay the same, oh no, it won't though. It won't though. Because if these values are the same, margin of error will get a lot wider. Think about what n will do. If n increases, margin of error will get wider. So if n increases and everything else stays the same, margin of error will get wider. So right now, if we resolve this, margin of error should be a lot wider. Because n increased and everything else stayed the same, margin of error would be smaller, right? So theoretically, and we're just doing theory here, theoretically it could be something like this. It should get smaller theoretically because you're dividing by numbers. But what we're saying is we want it to remain fixed. So we want it to stay the same. That's what fixed means. It's like fixed at 0.04. So what does this mean? Well, we don't control p hat and q hat. Those are just sample proportions, so we don't control what happened in the sample. We can't say, like, let's increase p hat. That's just not how it works. But we can say, let's use a different confidence. So as n increases, margin of error decreases. But as z increases, margin of error what's? If you increase z, margin of error what's? So z is what you're timesing it by. So if you increase z, making z bigger does what? Which is what they're alluding to in the first few questions. If you increase z, margin of error will do what? Like the value of margin of error on the other side will do what? Because you're saying this times this. So if you make z bigger, it'll make it wider. That's what differs. So do you see how these two things here would counterbalance each other? That's the key to this question. I'll change the color. I didn't like that. By doing a larger sample size, so it's going to increase the margin of error. It makes the interval wider, which means increased margin of error. So by increasing the sample size, you're getting a smaller margin of error. But by increasing the confidence level, you're getting a wider one. So you're kind of counterbalancing it. So you could keep the margin of error the same by increasing sample size and also increasing percent confidence right here. This is the plus or minus, correct? This is all the margin of error. Everything right here is the margin of error. Margin of error equals to p hat times q hat over n square root. And we use that as a plus or minus for p hat plus or minus I didn't do the z. Why didn't I do z? Z star. Z star times p hat q hat over n square root. There, right there. Little scribble. So this is very, very true. For a fixed margin of error, larger samples provide greater level of confidence. That is very true. Very tricky question. I think this one's easier. This one's really easy to show mathematically. This one seems tricky. It says, for a given confidence level, having the margin of error requires twice the sample size. So remember, the margin of error is always everything after the what? The margin of error is everything after what? The margin of error is everything after the what? Good quick review right here. You always can think, okay, the margin of error in this formula is what? It's everything after the what? Whenever you're looking for margin of error, you say, okay, wait, I just need to look after the what to see where the margin of error is at. Because you could literally call this p hat plus or minus margin of error. So the z-score is part of the margin of error. The margin of error is everything after the plus or minus. This portion over here is known as the standard error of p hat. And then the z star is the thing. So those are the two components. Everything after the plus or minus is the margin of error, like plus or minus this amount. And the p hat times q hat over n square root is the standard error. That is known as standard error. Good review and great job. Good to see you here, Julia. So the standard error right there is p hat times q hat over n. And then the margin of error is everything after the plus or minus. Always everything after the plus or minus. Let's throw some points, Julia. Good response. And so now, right here, let's take a look at this. That's the margin of error, right? So let's say I want to times this by 1/2. let's look at a little algebra right here. Great job, Lachey. Good practice. Can I just mathematically put this 2 inside this parentheses? Can you just mathematically do this and rewrite this as the following? This is algebra now. Can you just rewrite this as the following right here? Could I just rewrite that? 10b? Which one is it? 10b on the 201? Is it 201, Julia? Is it the homework? Can you do this algebraically right here? Awesome. We should be that to real soon here. Good question. Can you just do that right there? Is that allowed in algebra? Can you just do 1/2 and insert it into the radical? Algebraically, you can't. So what you have to do is you have to re-express this. What is square root of 1 over square root of 4? We actually can't. Don't worry, it's an algebra. No, just JK. What is square root of 1 over square root of 4? Like, what does that solve out to? What does square root of 1 over... It solves out to 1/2, right? Because... And that's just 1/4 square root. But you can also just put them both there. So this is also the same thing mathematically as this right here. And so think about this. Now, it can actually go inside the radical and be shared in that. So to get half the margin of error, you actually have to take what the sample? To get half the margin of error, because square root 1 over 4 equals 1/2. So to get half the margin of error, you actually have to take what the sample? To get half the margin of error, you have to take what the sample? It's like diminishing returns. Like if you want to decrease your margin of error by half, you actually have to take what the sample? Not a fourth. Take 4 times, because this is n times 4. Good answers there, Julia. So you actually have to take 4 times your sample. So you're trying to do 1/2 the margin of error, which requires 4 times the amount of sample. Like mathematically, to solve for half the margin of error, you have to have a n that is 4 times larger. Does that make sense conceptually? Like the math will give you a margin of error that's 1/2 your original margin of error if you increase your sample size by a factor of 4. So that's like diminishing return. It's like, well, I really want my interval to be a lot smaller on what I'm trying to estimate. And so we need 4 times the sample. And so it's just diminishing returns on samples, which goes to like taking data and stuff like that. So that's false. You see, it did it to me. It did it. Here we'll try to do number 9 real quick. Hopefully it's a short one. Okay, so this one we did earlier. It's just an interpretation, so we'll be doing 10 here in half a second. And we did this one earlier this morning, so I'm gonna do it a little bit more quickly. And then we only have 1 more question or 2 more questions. Thank you, Julia. Do you almost have this homework done? Question 9. So when you do these interpretations, write them down. I am blank % confident that the true blank is contained in the interval blank to blank. So let's see right here how to do it. Let's see. We are blank % confident that between blank to blank of the cars in the US are made in Japan. We're trying to estimate the true proportion. See, that's P. True proportion of cars made in Japan is contained. Got the hiccups. In the interval, I'm 90% confident. We are 90% confident that the true proportion of cars that are made in Japan that are driven in the US is contained in the interval 29 to 46.1. And try writing it down. Try practicing it, because that's going to be your real key to success. So have this written down right here. I am blank % confident that the true proportion of cars driven in the US that were made in Japan is contained in the interval blank to blank. Give your level of confidence, give what you're trying to estimate, and last but not least, give the interval values. So be able to write this down. My number 1 advice is to write these down. Write them down in the chat, write them down in your notes. You will be doing things like this on the final. So when you get to interpret this interval, practice it. And there's 3 intervals total. Check out the start of office hours where we did all 3 talking about the project. Just give a quick advertisement. If you want to start practicing your interval interpretations, go here to the start of office hours. And we already were doing the other intervals. Write them down, practice them out, and know how to do them. It's one thing to select the answer, but it's another thing to be able to say, I am 90% confident that the true proportion of cars that were made in Japan that are driven in the US is contained in the interval 29% to 46%. There we go right there. Okay, let's check out some question 10. Here we go with question number 10. Taking the note on it. Step 1, chapter 13. Homework. Question 10. Here we go. Okay. A customer advocacy group published a study labeling of seafood in 3 U.S. states. The study found that 12 of the 25 red snapper packages tested were a different kind of fish. So automatically we see 12 and 25. What are these values before we do anything down below? 12 is what and 25 is what? 12 is what and 25 is what? And they're trying to figure out the proportion of mislabeled. And great job, Julia, right there. They are X and N respectively. And from this, we could find P hat. That is X, that is N. And so because we want to know what proportion of mislabeled packages or what proportion of packages are mislabeled, and there it is, X over N is P hat. Are the conditions met? Did they randomly take them? I hope. Assume that they used a random sample. Good. Thank you for saying assume that. And these are probably less than 10% of all packages, which is good. The sample, let's see here. No, I would say yes. Let me go to yes. Yes, because the sample is a random sample. Good. The sample is less than 10% of the population. Good. And there are at least 10 successes, at least 10 failures. How many failures were there? So can you look at this visually and tell me how many failures there were? So who can tell me how many failures there were? Calculate the exact amount of 13 failures. Great job, Julia. That's correct. There were 12 successes and 13 failures right there. Now we need to construct a 95% confidence roll. I wonder, this is going to be crazy. Construct a 95% confidence interval for the true proportion where X is equal to 12 and N is equal to 25.
I found this on the web.
If it did that, my mind would have been blown. If it just like, here's the answer from Wolfram Alpha. So you could probably do Wolfram Alpha for this. So what's really great, and I'll show this, if I go to prop test, these answers are kind of close. It uses slightly different calculations than we use. And I got to change my digits back to 7. And this is a good guesstimate of what we should be getting. There's about the interval. This one doesn't use symmetric interval. Is it symmetric? It looks about. Uses chi-squared. So very close. 28 to 68 is what we should be getting. And that's why I like using programs like that to solve things nice and quick. Let's go ahead and solve this, though, and see how to get this. So to solve this, it really boils down to notation. So these questions right here are major notation checks to see if we know how to solve things with notation.
Notation, brother.
So the first thing we need to find for this is going to be what, Julia? What do we need to find a confidence interval to estimate the true proportion of mislabeled packages? What do we need to find first? Z-score. Yeah, let's find that Z-score. The Z-score is relative to how confident we are. So what is the Z-score for a 95% confidence roll? Go ahead and tell me the Z-score for 95% confidence if you know it. The Z-score for 95% confidence found on the David M. Lane is going to be 1.96. Great job, Lachey, too. Lachey and Julia right there. That is the Z-score, and the Z-score is relative to how confident we are. So when we hear this confidence level, the star means you pick the one based on confidence level. Now, the p-hat is going to be based on x over n. Sometimes they give us p-hat, sometimes they don't. But that's x, that's n. X over n equals p-hat. So p-hat is equals 0.48 because it's 12 over 25. And then what is q-hat equal to? Once you find p-hat, you want to find q-hat instantaneously. That's a q right there. So what is q-hat equal to? Make sure to know how to solve q-hat instantaneously when you get p-hat. It's equal to what? What is q-hat equal to? Perfect. 0.52. And it's 1 minus p-hat. So we're going to go down here, plug these in. 1.96 square root 1.52 times 1.4 or 1.48 over the 25 total sample, plus or minus 0.48, which was the estimate. Hey, what's up, Adam? Hey, Christian. Oh my gosh, got some of you who love it. And so now we go down here, we solve 0.52 times 0.48 divided by 25 square root times 1.96. And we just found the margin of error. Very close to the answers we were seeing Wonder if we would have got it if we used what I calculated. 0.198. Is that accurate? 1958. 1958. There we go. Nope. Keep changing my mouse setting. 0.48 plus 0.1958. There's that. And we go over here. There's the upper. And it looks like it wants it as a decimal. And the lower is going to be 1 minus. So we just take the value right there is 0.48, which is the estimate of the true proportion of mislabeled packages. And point. There we go. Check answers. We got it. And now I am blank percent confident that the true proportion of mislabeled packages for like all the fish is contained in the interval blank to blank. So it's not about one. One is 95% confident that between blank to blank of all red snappers. Oof. Okay. Here's the context we're looking for. In these 3 states, purchase. Oh my gosh. Okay. What's the small difference? Consumer post living of seafood sold. So it's sold. Oh, they're saying purchase for the study. No, it's not purchase for the study because that's what we saw in the study. So yeah, and then they ask you to convert to percentages. If you don't convert to percentages, just let me know. Yeah, it's for the truth for everything. It's not the ones purchased in the study because we know what the sample is. So yeah, Christian. Yeah, I haven't seen you in a while. I just realized. Yeah, let me throw some points. Thank you for being here. How's everything going by you? So this is the truth for all. We already know the answer for the sample, which is 48%. We want to figure out the truth for all. So that's trying to figure out the truth for all the red salmon, red snappers, and all that stuff. So does that make sense, Julia, right there? It's not about what was in the study because we know 48% in the study were mislabeled. So we wouldn't talk about the study right here, which is the answer down here. The red snapper purchase for the study we know is 48% mislabeled. We want to know for all that are purchased everywhere. So we're trying to estimate the truth for everything. And we'd say probably between about 28.4 to 67.6% of all red snappers mislabeled. We know for the study it was 48% because that's our p hat. So I wish they said that at the end. That kind of some great stuff. This last one right here is a really good one, but requires a lot of work on the notation and requires some small decimals. Stats, is that a code? We got the stats code, Christian? Have I forgotten about that? Christian knows all the old codes. How's everything going, Christian? Like, what are you up to? If you want to share, it's your call. So let's say right here. Okay. Last question is all about notation. The campaign, yeah, we just added this in like a week or 2 ago. And it was thanks to Adam Breimer, who's the Director of Technology and Enhanced Education. Are you trying to find out your rank or your points? Exclamation mark points. Check out those points. So, but I reset the points. So there's my points. I'm at ultimate Blake level. I might be on meme tier. I think meme tier is 10 million now. So let's find our notation, brother.
Notation, brother.
We got p hat plus or minus z star based on percent confidence. P hat q hat over n square root. So the first thing to notice right here is the sample size n is very large. We're going to get some very small decimals on this. The x, which we don't even have right now, so we need x over n. We know what n is. And then we have x right there, which is the number of successes equals to p hat. And 1 minus p hat equals q hat. I've started like coloring things. I think it helps. Had end of the year presentation for Torch Funds last Friday. Now it's time to... That's awesome. Congratulations. I started marking notation by coloring it, and I think that's really helped people track what I'm doing to be like, okay, this value is here, because there's a lot on the screen at times. So the values we're using will be tracked across. We need to find p hat here in a moment. Q hat will be in the formula here. And p hat's over here. And then the z is relative to the confidence, which the z-score will do some light purple here. Light purple. confident. Okay. So now we just need to find these values right here. P hat's going to be the first one we find. 1 minus P hat is Q hat, or excuse me, X over N. So just moving the decimals. 4781 divided by, so it's going to be 4.78%. Remember to do it as a decimal here to start. So that is P hat right there, X over N. I'll write in the numbers. 4781 over. There we go. And so that is 0.04781. The Z star is going to be found via the David M. Lane applet. So make sure to go to the David M. Lane applet or look at the number we give you on the test. It's going to be 1.96 for 95% confidence. Here it is right here. Make sure you've clicked the second button. Make sure you click between and enter in 90 or 95 if you're doing a 95% confidence roll, and use the 1.96. Since we're doing plus or minus, it'll already include the plus or minus on it. And there's the Z star right there, 1.96. Star meaning you get to pick it, Z based on the normal curve with the standard normal. And then next we have the same P hat we just found. So the P hat we just found is 0.04781. And then we times that by the complement, which is going to be 1 minus it. There's the complement, Q hat. Divide by the sample size. And there we go. There's the math. Let's go ahead and solve this. Here we go. And so let's do 1 minus. There we go. Times it. There's P hat times Q hat. Basically the same as P hat. Divide by sample size. Square root turns into a ridiculous decimal times 1.96. And that is the margin of error, 0.001322. 0.001322 plus or minus 0.04781. So there we go. Very small decimals. Watch out. And I think it wants it as a percentage. So we're going to times it by 100 now. This would be 4.7. Let's do the little 4 a little better now. 4.781 plus or minus 0.1322. And so then we can get the upper and the lower by subtracting on this. We'll times that by 100. And so now we go right here and go 4.781 plus that, 4.913. And the lower on the interval is going to be that minus that. So 4.781 minus 0.132, 4.6488. There we go. So now that we have our numbers, let's go check out the work. We've got the work and the numbers, 95% confident at 2 decimals. Let's grab our work over here. 4.91. Go 4.91. 4.65 was the other one. 4.65. I think we've done it right. Ooh, good. Okay, good job. Given, do you think 4.5 is possible? No, it's not in my interval. The true proposed rate is not plausible, or the proposed rate is not true. The proposed true rate is not plausible because my confidence roll does not contain that value. Is that? There we go. We've done the full homework, and that's a lot of good work. So really excellent work if you followed along and did all the homework questions. We did mark number 11, right? Oh, we didn't mark it. Oh my gosh, we didn't mark number 11. Take a guess right here at the time on it. I was like, I don't remember marking it. Chapter 13, homework, question 11. Well, that's got it. A lot of good work today. All the questions, all the homework done. So make sure to practice. You're welcome, Lishay. Did you get that 100, Lishay? Great work. Remember, we saw that doing the work is a big portion of success. Good job, Julia. Check out the other questions if you want. That's all the homework. Every homework question has now been done in this video. So check it out. And we tried to talk through the theory of it too, so that way you can better understand it. It's not just about solving these questions. It's about understanding, like, well, what are we trying to solve for? We're trying to find the true proportion of people who respond to this mailer. So from the 100,000, we get an idea, which I guess they got a really big list because they need to at least have 1 million people to not violate the 10% condition, which states we need to sample less than 10% of the population. We have at least 10 successes, at least 10 failures. So a lot of things like your conditions, your formulas, your notations are the keys to success. And until next time, bye for now, everyone. Bye.